Atlas is not where it's supposed to be. On October 29, 2025, as the interstellar object Atlas passed through perihelion, the most sensitive radio telescope array on Earth detected something that should be impossible. The Atacama Large Millimeter Array, one of the most powerful astronomical instruments ever built, measured Atlas's position with extraordinary precision. And Atlas was in the wrong place. It was 4 arcseconds away in right ascension from where gravitational physics predicted it should be. 4 arcseconds might not sound like much, but at the distance Atlas was from Earth, this represents a deviation of tens of thousands of kilometers from its expected trajectory. Something pushed Atlas off course. Something accelerated it in ways that gravity alone cannot explain. Today, we're going to dive deep into what this non-gravitational acceleration means, how scientists calculated what would be required to cause it naturally, and why the answer to a simple question in the coming weeks will determine whether we're looking at an exotic comet or our first confirmed extraterrestrial spacecraft. Let's start with some quick background. Atlas is the third interstellar object ever detected, meaning it came from beyond our solar system, traveling through the void between stars before entering our cosmic neighborhood. It was discovered on July 1st, 2025, moving at an incredible 58 kilometers per second, with an estimated diameter of 5 kilometers. That makes it 1,000,000 times more massive than Oumuamua, the first interstellar visitor, and 1,000 times more massive than Borisov, the second. It's enormous by interstellar object standards. Over the past 4 months, Atlas has accumulated 9 statistical anomalies that challenge our understanding of natural comets. Its trajectory aligns perfectly with our planetary disk. Its composition resembles industrial alloys more than cosmic ice. It arrived from the same direction as the famous 1977 WOW signal, and it's been exhibiting behaviors that don't match any known natural processes. Harvard astrophysicist Avi Loeb, former chair of the astronomy department and one of the most cited scientists in the field, ranks Atlas as a 4 on his scale from 0 to 10, where 0 means definitely natural and 10 means definitely technological, but until October 29th. There was always room for natural explanations. Unusual? Yes. Statistically improbable? Absolutely, but not impossible. The non-gravitational acceleration changes that calculation. Here's what happened. As Atlas reached perihelion at 7:47 a.m. Eastern Time on October 29th, positioned 203 million kilometers from the Sun, ALMA was tracking its position with extreme precision. Radio telescope arrays like ALMA can measure positions down to tiny fractions of an arcsecond. When they compared Atlas's actual position to where gravitational models predicted it should be, there was a discrepancy. Atlas had accelerated, not just in one direction, but in 2 distinct components. First, a radial acceleration away from the Sun at 135 kilometers per day squared. This pushes Atlas outward, away from our star. Second, a transverse acceleration perpendicular to the Sun's direction at 60 kilometers per day squared. This pushes Atlas sideways relative to its orbital path. Let me put those numbers in perspective. Over the course of 1 month, this acceleration will cause Atlas to deviate from its purely gravitational trajectory by about 60,000 kilometers. That's roughly 10 times the radius of Earth. It's not a tiny effect. It's measurable, trackable, undeniable. The question is, what's causing it? There are only 2 possibilities. Either this is natural outgassing, the rocket effect from sublimating ice ejecting gas and pushing the object, or it's artificial propulsion, an engine or thruster system actively controlling the trajectory. Let's examine the natural explanation first. And this is where the physics becomes really interesting. As soon as Avi Loeb heard about the ALMA results, he did a calculation using momentum conservation. This is fundamental physics, one of the most basic principles in all of science. When something accelerates, when it gains momentum in one direction, something else must gain momentum in the opposite direction. Action and reaction, Newton's third law. If Atlas is accelerating because it's ejecting gas, then the mass of that ejected gas, multiplied by its velocity, must equal the mass of Atlas multiplied by its acceleration. This is momentum conservation. The equation is straightforward. Here's what Loeb calculated. The force acting on Atlas equals its mass times its acceleration. That force comes from gas being ejected at some velocity. Using momentum conservation, you can solve for how long it would take Atlas to lose all its mass through this process. The answer depends on how fast the gas is moving. For typical cometary outgassing, gas sublimates from the surface at thermal velocities, which at Atlas's perihelion distance would be a few hundred meters per second. Let's say 200 to 300 meters per second. When you plug in the measured acceleration of about 0.02 millimeters per second squared and assume thermal gas velocities, you get a total evaporation time of less than 6 months. Let me repeat that. If this acceleration is caused by natural outgassing, Atlas would completely evaporate in less than 6 months. But it gets more specific. Atlas took about 1 month to cross through the perihelion region, the zone where it experienced maximum solar heating and where this acceleration was measured. 1 month is about 1/6 of 6 months. Therefore, if the acceleration comes from natural processes, Atlas must have lost at least 1/6 of its mass during that 1-month period. 1/6 of its mass in 1 month. Now here's where this becomes critical. We have other measurements of Atlas. The James Webb Space Telescope observed Atlas for 5 months before October 2025 and measured a mass loss rate of 150 kilograms per second. That sounds like a lot, but it didn't produce any detectable non-gravitational acceleration during those 5 months. This allowed Loeb to calculate Atlas's minimum mass. If 150 kilograms per second of mass loss doesn't create detectable acceleration, then Atlas must be extremely massive. The calculation gives a minimum mass of 33 billion tons. 33 billion tons. That's the lower bound on how much Atlas weighs. So here's the mathematical problem. If Atlas has a mass of at least 33 billion tons, and it lost 1/6 of its mass in the perihelion month, then it shed at least 5.5 billion tons of material. 5.5 billion tons of gas and dust ejected into space in the span of about 30 days. That should create a massive, absolutely enormous cloud of material surrounding Atlas. We're not talking about a subtle effect. We're talking about billions of tons of gas expanding outward from the nucleus, creating a coma so large and bright it would be unmistakable in any observation. And that's the test. That's how we determine if this acceleration is natural or artificial. If the acceleration comes from outgassing, there must be a massive cloud. If we observe Atlas in November and December with all our most powerful telescopes, and we don't see a cloud anywhere near large enough to account for 5.5 billion tons of ejected material, then the natural explanation fails, and we're left with only one alternative. The acceleration is artificial. Now, Mapper, before we discuss what artificial means, we need to talk about Oumuamua, because this isn't the first time we've seen this exact scenario. Oumuamua, the first interstellar object ever detected back in 2017, also exhibited non-gravitational acceleration. As it traveled away from the Sun, it accelerated faster than gravity alone could explain. Scientists expected to see cometary outgassing, a tail or coma that would account for the acceleration, but there was nothing. Deep observations with the Spitzer Space Telescope, one of the most sensitive infrared instruments ever built, found no sign of gas or dust around Oumuamua. Zero. Nothing. This created a major problem for the natural explanation. How do you have cometary acceleration without a comet's tail? Some scientists coined the term dark comet to describe Oumuamua, a comet that doesn't show a visible tail. But here's the issue with that terminology. A tail is the defining signature of a comet. It's what makes a comet a comet. Saying dark comet is like saying invisible light or silent sound. It's an oxymoron, a contradiction in terms. Avi Loeb makes a powerful analogy about this. He says, imagine a cave dweller who has never seen modern technology encountering a cell phone. The cave dweller might classify the cell phone as a rare type of rock because that's the only framework they have. They would call it a glowing rock or a singing rock, adding adjectives to force the unfamiliar object into a familiar category. But the cell phone isn't a rock at all. It's something from an entirely different category: technology. In the same way, calling Oumuamua a dark comet might be forcing an artificial object into a natural category simply because we don't have the framework to accept what we're actually seeing. And now, Atlas is following the same pattern. Non-gravitational acceleration without the expected massive outgassing. If this holds up, if December observations don't show the required 5.5 billion ton cloud, then we have two interstellar objects, both exhibiting acceleration, both lacking the natural explanation. At that point, the simplest explanation, the one that fits all the data without invoking multiple unprecedented natural processes, is that we're looking at spacecraft with propulsion systems. So what would artificial propulsion look like? What would it mean for Atlas to have an engine? First, the acceleration we're measuring is modest by rocket standards. It's not a massive burn, it's a gentle, sustained thrust. Over 1 month, it changes the trajectory by 60,000 kilometers. That's enough for course corrections, for fine-tuning a path through the inner solar system, but not enough to dramatically alter which planets Atlas approaches. This is exactly what you'd expect from a navigation system. Not a main engine for interstellar travel, but a guidance system for maneuvering through a stellar system. Small adjustments to optimize the trajectory. Second, the timing is perfect. The acceleration occurs at perihelion, the moment when Atlas is closest to the Sun and has maximum solar energy available. If Atlas uses solar power, this is when its power systems would be at peak capacity. It's the ideal time to fire thrusters for course corrections. Third, the dual component acceleration, both radial and transverse, indicates directional control. Natural outgassing tends to be more random, following the rotation of the nucleus and the distribution of volatile ices. But this acceleration has specific components in specific directions, suggesting deliberate thrust vectors. Fourth, there's the blue color anomaly. Observations during perihelion show Atlas getting bluer than the Sun, which should be physically impossible for a cold natural object. But a hot engine, an electric propulsion system, a plasma thruster. These could emit light in the blue spectrum. The color and the acceleration could be directly connected, both signatures of active propulsion. For comparison, our most advanced spacecraft use ion drives that produce gentle, sustained thrust over long periods. NASA's Dawn mission to the asteroid belt used ion propulsion to maneuver between multiple targets. The acceleration levels are similar to what we're seeing with Atlas, modest but sustained, allowing precise trajectory control. If Atlas is artificial, its propulsion system would represent technology far more advanced than ours, but the basic principle would be the same: controlled thrust for navigation. Now, here's what happens next, and why the coming weeks are absolutely critical. November 4th, just days from now, ESA's JUICE spacecraft makes the first post-perihelion flyby of Atlas, passing 64 million kilometers away. JUICE carries sensitive instruments designed to study planetary atmospheres and detect gases. If Atlas shed 5.5 billion tons of material, JUICE will see it. JUICE will capture images of Atlas's coma, measure its brightness, and analyze spectroscopic signatures to determine what gases are present and in what quantities. This is the first test. If there's massive outgassing, we'll know within days. But November 4th is just the beginning. The real definitive observation comes on December 19th, when Atlas makes its closest approach to Earth at 269 million kilometers. At that distance, hundreds of ground-based telescopes will observe Atlas simultaneously. The Hubble Space Telescope, which has imaged countless comets and can detect even faint dust, will capture high-resolution images of the nucleus and surrounding material. The James Webb Space Telescope, the most powerful infrared observatory ever built, will measure thermal signatures and molecular composition in extraordinary detail. Webb can detect the faintest traces of water vapor, carbon dioxide, and other volatiles. Between November 27, 2025 and January 27, 2026, the International Asteroid Warning Network, IAWN, will conduct an intensive monitoring campaign. This is unprecedented. IAWN is designed to track objects that threaten Earth, extinction-level asteroids. They don't waste resources on interesting scientific curiosities. The fact that they're dedicating 3 months of intensive observation to Atlas, an object that cannot possibly impact us, tells you how seriously the scientific community is taking this. During this campaign, dozens of professional observatories around the world will track Atlas continuously, building up a comprehensive data set of its brightness, its spectrum, its trajectory, and most critically, whether there's a massive cloud of gas surrounding it. The question is simple. Will we see 5.5 billion tons of ejected material, or won't we? If we do see it, then the natural explanation holds. Atlas is an unusual comet, perhaps with exotic composition or unusual volatility, but fundamentally natural. The non-gravitational acceleration came from massive outgassing at perihelion. Mystery solved. But if we don't see it, if December observations show Atlas without the required massive cloud, then we have a major problem. We have measured acceleration without the natural mechanism to cause it. At that point, we'd be looking at the same situation as Oumuamua. Non-gravitational acceleration, no cometary tail, no visible outgassing sufficient to explain the thrust. 2 interstellar objects, both accelerating, both lacking natural explanations. And the simplest conclusion, the one that doesn't require inventing multiple unprecedented natural processes, is that these are spacecraft. Avi Loeb has written 11 scientific papers on Atlas in recent months, analyzing its trajectory, its composition, its anomalies. His conclusion is careful but clear. We need to take seriously the possibility of artificial origin. The data is pointing in a direction that cannot be ignored simply because it's uncomfortable or challenges our assumptions. As he emphasized just yesterday in a different context but with direct application to Atlas, it is bad professional practice for theoretical astrophysicists to conclude that the data must be wrong just because they do not have a theoretical explanation for it. The data is showing non-gravitational acceleration. The data will soon show whether there's massive outgassing to explain it. And if that outgassing isn't there, we need to follow the data wherever it leads, even if that means accepting that we're observing technology from another civilization. The implications are staggering. If Atlas is artificial, if it has a propulsion system, then we're witnessing an active extraterrestrial mission in our solar system. Right now, present, observable. A civilization capable of building a 5-kilometer spacecraft and sending it across light years would possess engineering capabilities centuries or millennia beyond our own. The fact that it's maneuvering at perihelion, making course corrections with precision timing, suggests not just technology but active guidance. This wouldn't be an ancient derelict drifting through space. This would be a functioning probe executing a planned mission. But we're getting ahead of ourselves. The data will provide the answer. Science will deliver the verdict. And we don't have to wait long. November 4th, JUICE makes contact. First post-perihelion observations arrive. We get our first look at what perihelion did to Atlas. Whether there's increased brightness, whether there's an expanded coma, whether material is streaming away from the nucleus. December 19th. Closest approach, hundreds of telescopes, Hubble, Webb. Ground-based observatories, all focused on one object, all looking for the same thing. Is there a massive cloud of gas? Or isn't there? By Christmas, we'll have the answer. By the end of December 2025, we'll know if the non-gravitational acceleration of Atlas has a natural explanation, or if we need to seriously consider that we're looking at our first confirmed extraterrestrial spacecraft. This is not speculation about distant possibilities. This is not theoretical discussion of alien life in abstract terms. This is a concrete object in our solar system right now, exhibiting measured acceleration that demands explanation. The mathematics are clear. The observations are coming. The data will decide. In just a few days, JUICE begins sending back images. In a few weeks, the full power of Earth's astronomical infrastructure turns toward Atlas, and then we'll know. Are we looking at an exotic comet with unprecedented properties, or are we witnessing the first confirmed visitation by extraterrestrial technology? The acceleration has been measured. The test has been defined. The observations are about to begin. Stay tuned. Because November 4th is less than a week away, and what JUICE reveals could be the first piece of evidence in answering one of humanity's oldest questions. Are we alone? Or has something come to visit us from the stars? The non-gravitational acceleration of Atlas is about to give us the answer. Subscribe and turn on notifications. Because when those first JUICE images arrive on November 4th, when we see what Atlas looks like after perihelion, you'll want to know immediately. The data is coming. The truth is coming. And we're about to witness history together.